There's a lot going on in this thin lens equation diagram. Let's see if we can unpack it. What I've included here is the standard three principal rays that are drawn for a converging lens. Focal length is positive. In the situation where the object distance s is greater than the focal length here. Okay, so our object gives us these three principal rays that we've seen in the previous videos. What we're able to do is to pick out some triangles that are formed by the various pieces of this diagram and find a relationship between the object distance from the lens to the object, the image distance from the lens to the image, and the focal length from the lens to the focal point. The lateral magnification is the first definition we should get out of the way. That is simply the image height, lateral or perpendicular to the optic axis, divided by the object height over here. So y prime divided by y. Well, we have similar triangles. The first is formed by the object and the object distance here, this triangle. So I've labeled this opening angle alpha. The other triangle is formed by the image distance, y prime image height, the s prime image distance, and this hypotenuse. So that angle is an opposite interior angle formed by the optic axis and principal ray 3. Alphas are the same in both triangles, therefore the tangent of alpha in this triangle is y over s, in that triangle is y prime divided by s prime. In fact, we have to stipulate that it's minus y prime because y prime is already negative below the axis. And we want to end up with the same positive angle or positive tangent. So that definition, you can see y prime divided by y, you just rearrange this or cross multiply if you want, works out to be negative s prime image distance divided by object distance s. We have to pick out some different triangles here to come up with our relationship with the focal length. You can see there's another triangle, a right triangle formed by the object height mapped over to the lens, the focal length here, f, and this hypotenuse, so I've labeled that as beta. And then we have a similar triangle opposite with the same beta. Okay. Now the distance from the focal point, the primary focal point to the image, is s prime image distance minus the focal length. Right, so this distance here is s prime minus f on that leg of the triangle, and we have this positive distance is negative y prime. So we'll play the same game with the tangent of these angles. Tangent beta is equal to y over f, and it is also tangent beta equal to negative y prime divided by s prime minus f. So there's a little more algebra to pick out this result. The ratio y prime over y is f minus s prime, you flip the sign to make everything positive, divided by f. But that's lateral magnification, so we can bring in that result here and say y prime over y is minus s prime over s, and then work on this equality, giving us 1. You divide this f into f, so we have 1 minus s prime over f equals negative s prime over s. From here, We can simply divide both sides by s prime, the image distance. You end up with 1 over f minus 1 over s prime is equal to 1 over s. And the form of this thin lens equation that you usually run into will be 1 over focal length equals 1 over object distance plus 1 over image distance. To succeed in applying the thin lens equation, you're going to need to follow some sign conventions. So with our equation, we're going to be inserting both positive and negative values for these three variables, f, s, and s prime. And we have to be a little loose with what we're calling focal length or object and image distances. Usually we talk about these things as if they were positive quantities, but these variables going into the thin lens equation must carry a plus or minus sign, and you have to be very careful with the plus or minus sign in order to come out with the correct solutions. For focal length, we've already laid out the rules. If you have a converging lens, f is positive. Diverging lens, f is negative. More importantly now, the object distance, s, will be positive if the object is on the same side of the lens as the incoming light rays. That will always be true if you have only one lens in your problem. S will always be positive, regardless of whether the lens is converging or diverging. Now, we'll look at cases in class and in the lab experiment where you have more than one lens operating on the light. You could end up with a situation where we would call the object distance negative because the object will be on the opposite side of the lens as the incoming light rays. The only way to make that happen is if you create an image using the first lens and you use that image as the object for the second lens. In those problems, you may see situations where the object distance is negative. We'll do some of those in class. Finally, for the image distance, you need to follow a similar set of rules. The image distance will be positive, s prime, if the image is on the opposite side of the lens as the incoming light rays. And the image distance, s prime, will be negative if the image is on the same side of the lens as the incoming light rays. So for the single lenses, the only way s prime will be positive is if you have the converging lens with s greater than f. That was our one real image. The other three situations in that diagram all gave us virtual images. So every situation with a diverging lens, regardless of the relationship between s and f, will give you a virtual image, and s prime will be negative. You can also get a virtual image with a negative s prime if you place the object closer to the lens than the focal length. Again, that is restricted to the use of a single lens. When you have multiple lenses involved, we have to be careful with our signs as usual. Join me in class and we'll learn how to master the thin lens equation and prepare for this lab experiment.